Hello and welcome back on the Mattoni channel. This is Do It Lagrangian, and in today's episode we will treat the Atwood machine, which in Italy we simply define as a pulley with two masses and a cord. So let's go. So we will consider a pointwise pulley because we don't want to have situations which are too much complicated for these cases, but we will introduce a more complicated scenario later. Okay, so we imagine to have this pulley with two masses, M1 and M2, and we know that for each masses we have a weight force Fw1 and Fw2, and since the cord has a fixed extension, we can say that every mass is subject to the tension of the cord, which is the same for both the body. Okay, so both bodies are subject to the same tension. Indeed, we have A1 equal to minus A2. Okay, so we can just say, letting the index 1 or 2 drop, A1 equal to A for simplicity. So we have two equations of motion, because we have two body, and those two equations will be only through the y-axis. Okay, so only amongst the y direction, because this is a monodirection problem. Okay, so for the first body we will have Fw1 plus T equal to M1 times A, and for the second body we will have Fw2 plus T equal to Mw2, and in this case we would have to write A2, but A2 is equal to minus A1, and so this is minus A. Okay, now if we do our projection among the y-axis, we will have 1y and 2y equations, which are minus Fw1 plus T equal to M1 times A, and minus Fw2 plus T equal to minus M2 times A. Okay, and now what we have to do is to solve this problem for T and A, which are our wanted values. Okay, and we know that Fwi is equal to m of I times g, where g is the gravitational acceleration, and in this case I is only going through 1 and 2. So what we can do is subtract those two equations and obtain F minus Fw1 plus Fw2 equals to M1 plus M2 times A. Now substituting this relation for Fw1 and Fw2 and introducing the mass difference delta m equal to m2 minus m1 and the total mass m tot equal to m2 plus m1, we can write delta m times g equals to m tot times a. Okay, and we can also, in this case, find the acceleration, because we can divide both sides by m tot and have a equal delta m over m tot times g. Okay, and now we can substitute our acceleration in the first or in the second equation. So now substitute, for example, a in the equation 1y, which will be minus m1 times g plus the tension equal to m1 times delta m over the total mass, and here we have times g. So we can now isolate the tension, so T will be equal to, we are going to transport this term on the other side of the equation, and we will have m1 times g, which is common to both the terms, times 1 plus delta m over the total mass. And now if we do the minimum common denominator, we have m1 times g times m tot plus delta m. Okay, and this is just over the total mass. We can do another calculation here, and if we substitute m total and delta m, we can write m1 plus m2 plus m2 minus m1 over the total mass, which we don't write explicitly. Now what we can see is that m1 and m1 cancels out, and what remain is T equal to 2 times m1 m2 times over the total mass, okay, times g. And we have just found out that the tension depends on the reduced mass of the system mu, which is m1 times m2 times over the total mass, and this is just the reduced mass of the system. Okay, so we can write our tension as T equal 2 times mu times g, and this is a very elegant result. So this is for Newtonian mechanics. So now we want to go from Newtonian to Lagrangian. Okay, and we have to define the Lagrangian of our system. We know that our Lagrangian is equal to the kinetic term minus the potential term. In this case, the kinetic energy is equal to 1/2 m1 times v1 squared plus 1/2 m2 times v2 squared. And we will see later why I don't write just v1 equal minus v2 plus obviously a constant and so on, and this is obviously a vector. Okay, and this can be made null. Okay, but we can see it later. Okay, so this is for the kinetic term, and for the potential term we will have V equals to m1 times g times y1, which is the height of the first body, plus m2 times g times y2. Okay, and in this case our L can't let us evaluate the tension. So we have to introduce a constraint in this case, because it's only one, and this is due to the chord. Okay, because we know that if there is m1 and this is the y direction, this is the height y1, this is y, and here we have the 8 y2, we at least could have an offset between our two body, but this does not change the physics of the system nor the equations, because if we do the a derivative in terms of a constant term, it will vanish out. So what we have is that since a1 is equal to minus a2, we can project amongst y direction, okay, and have a1 equal to minus a2, which if we integrate, okay, in terms of the time, conduct us to v1 equal to minus v2 plus eventually v02, which is 0 because we suppose the two bodies initially at rest. Okay, so if we integrate another time, so another integral in terms of the time, since v1, okay, this is just dvi in dt with I equal to 1, and so this is y1 equal to minus y2 plus that offset we discussed earlier. Now we can introduce, so we have found the constraint, okay, phi of y1 y2, which is equal to y1 plus y2 minus y0. Okay, we just take everything to the left, so we obtain a term which is 0 for every y1 and y2. Okay, so for every combination of the two. Okay, so we can write it like this. Okay, and now we can introduce the Lagrange multiplier lambda, which is a real number in this case, and L prime, which will be our new Lagrangian, which is equivalent to the first one since phi is 0 every time, but its derivative will be different than the one of L. So we add lambda times phi, okay, and now we can solve the Euler-Lagrange equation. So now we can solve Euler-Lagrange equations. Okay, in this case we will have d in dt, total derivative, times of dl prime in the yi dot minus del prime in the yi equal to 0. Okay, and for I which go from 1 to 2. So we obtained a system of two differential equation, and we can evaluate these equations term by term for simplicity. So if we call this part A and this part B, we can say that A, which is d in dt dl prime in the yi dot, and recall that v of I is equal to y of I in this situation, because the movement of our body are only vertical, so only amongst the y direction. So here y which goes from 1 to 2, what we can have is the in dt 1/2 m of I, okay, times 2 v of I, okay, because we simply derive in terms of yi dot, and this is the, if we do simply the time derivative and cancels out, and the 2 cancels out, okay, we can have m of I times yi double dot. So now the b term is a little bit different, but not so much. So del prime in the yi will be equal to, so we first differentiate the potential part, which in this case we have written here. So for simplicity, let's just write it as d in the y. In this case we can just write v or minus v plus lambda phi, because those are the only two terms which don't vanishes for the derivative in terms of yi. Okay, so now the potential term will just give us minus m of I times g, and the Lagrangian multiplier term will give us, okay, plus lambda. Okay, so our Euler-Lagrange equations in this case, because they are plural, okay, sorry, I have used badly my space, okay, so here and here will be m of I, in this case just m of 1, times, also here we can write a1, okay. Now we have minus this term, okay, because the Euler-Lagrange is like that, so we have to change all the signs. So we can write plus m of 1 times g, sorry, a little bug of good notes. Okay, this is good. Okay, m1 times g minus lambda equal to 0, and here we will have m2 times a2 plus m2 times g, okay, minus lambda equal to 0. And only now we use the relation we mentioned earlier, so that a1 is equal to minus a2, and that a1 can just be named a, as we have done before in the Newtonian part. So what happened here? So this is 1, this is 2, this is m1a plus m1 times g minus lambda equal to 0. This will be minus m2 times a plus m2 times g minus lambda equal to 0. Okay, and now, like before, we can just do the first equation minus the second one to have the total mass times the acceleration minus the difference between the two masses times g equals to 0. Okay, I've skipped some passages just because this equation is a lot like the Newtonian one. Okay, and this lambda will have the dimension of a force. Okay, so we will only have to take care for his sign when we finish our calculation. So here we can find the acceleration of the system, which will be equal to dm over the total mass times g, and then we can substitute this into the second equation, for example, to make it clear that it makes no difference in which of the two equations we substitute our relation. So now we have minus m2 times delta m over m tot times g plus m2 times g minus lambda equals to 0. Okay, and now our lambda will be equal to m2 times g times, in this case we have also changed the sign because we isolated the minus lambda, so what we obtain is, okay, 1 minus delta m over m tot, okay, which reduces to m2 times g times m tot minus delta m. Okay, and now m total minus delta m is just equal to m1 plus m2 minus m2 plus m1, because we have to change the sign of the difference, and this will be equal, since the two m2 cancels out, to 2 times m1, and so we obtained again lambda equal to 2 times m1 m2 over the total mass times g, and we have found here the exact same result as the one obtained in the Newtonian way. So we can say this is our reduced mass. Okay, and we can write in the end lambda equal to 2 times mu times g, and our tension can be written as a vector of the plane as open parenthesis equal to 0 comma 2 times mu times g. Okay, because is a vector which have the same direction of the y-axis. Okay, this is our final result. Thank you for the attention. If you have liked this episode, please like, and if you want, subscribe to have more material like this. And if you have any idea of some possible physics problem I could treat using the Lagrange mechanics, please write it down in the comment. Maybe next I will treat the harmonic oscillator. Okay, thank you.